Okay, so for our improper integrals, like I said, we have two different types. Type 1 is going to be where one or both bounds is infinity. Okay. Type 2 is that the function is discontinuous in the interval of the integral. And these are both classified as improper integrals. Basically, they are not in a form that we've been able to evaluate them up until this point. So, like I said, if we're dealing with infinities here, right? I'm either dealing with a bound that's in infinity, or I'm dealing with a graph that has an infinite behavior. Yes. And what other operation have we talked about in this class that lets us deal with infinite behaviors? Limits. Okay. So we're actually going to change these basically into two separate problems. We're going to have an integral problem, and then we're going to have a limit problem. And so that's how we're going to get around those infinite behaviors. So you don't have to write all this down. So for type 1, which is what we're going to look at today, which is where one or both of my bounds are infinity, okay, we're going to have two different things that could happen. Okay, so like I said, we're going to have this infinite behavior. And so the way that we're going to get around that is that we just want this to be a normal bound so we can treat it as an integral problem. So we're going to say that instead of infinity, we're going to change this to b. However, it's still going to be going towards infinity. So now this is my integral problem. And then on the outside is where I'm going to make it into a limit problem by sending that top bound to infinity. The same would be true if it was negative infinity, right? I'm just going to let it be my bottom bound instead, okay? Now, the way that we have to get around it, if both our bounds are infinity, is we're going to have to break it up at some c value, right, in between. Usually we pick a strategic value. A lot of times 0 is helpful, or like 1 or -1, depending on what the function is. And then basically we would create two different limit problems within that. Are we all with me there? Now, the other thing that we have to think about is that if I have limits that are going towards infinity, do all of our infinite limits, I said some of them get an answer, but do all of them get an answer? No, like with my x squared, right? If I looked at the limit as x goes to infinity of x squared, what does that equal? What is my y value going towards? Infinity, right? So if we end up with a limit that does not exist, that means that it diverges, meaning that I don't have an answer. So in order for the integral to have an answer, the limit has to exist. And we would call that converging to a specific value. Now, on the last case, because you're going to have two limits, right, both limits are going to have to converge or exist in order for the whole integral to work. So like if one of them doesn't work, then the whole thing doesn't work. Are we all with me there?
Yes.
Questions so far? Okay, some people are still writing. Oh wait, 1 second. just so you know, like we can make these variables be whatever we want them to be. I tend to stick with A's and B's just because we're really familiar with A's and B's when we talk about bounds. Yes, so then it's a little bit easier to keep track of. If my bottom bound is the one that's infinity, I'm going to make it A. If the top bound is my one that's infinity, I'm going to make it B, which is then, again, extremely helpful. If you have both bounds at infinity, it's easier to keep track of the A and the B because you know which one is which. Does that kind of make sense? But if you want to use other variables, you can. Just be careful with them. So, a couple of hints, okay? One, we are going to treat this as two separate problems, which I kind of talked about. We are first going to evaluate an integral once we have changed our bounds, and then we will evaluate our limit. Okay, if you start trying to do too many things at once, okay, it gets a little confusing. Also, that's why I like to go ahead and go over to the side, do my integral work first. That way then I don't have to write the limit as b goes to infinity 400 times as you're writing out your integral steps. Okay, so that's why I said treat as two separate problems. Also, the other thing that we want to keep in mind is we want integrals to be improper in only one place. Meaning that if my top and bottom bound are both infinity, that's why we have to split it up. We won't look at any like this, but technically, like if you also had like an infinite bound and the function was discontinuous, you would also need to split that one apart, okay? Because we only want it to be improper in one place. If it's improper in more than one place, then we have to split it into separate intervals. Now, next up, this should look familiar. This is actually what I just showed y'all. Okay. So I have the integral from 1 to infinity of 1 divided by x to the p power. So let's think about what that represents. Okay. Again, at the end of the day, we can't plug in infinity, right? But we're going to be taking an infinite limit, okay? So we're going to be plugging in, quote unquote, infinity into our denominator there, yeah? Yes, no, maybe? Okay. And in order for us to have a convergent limit that has a fraction, right? That means that my top has to be smaller than the bottom. Yes? No, maybe? Because if I have a number over an infinitely big number, yes, that whole fraction would just be getting closer and closer to 0. Are we okay with that? So, what that means for us is that this integral will be convergent as long as that p-value is greater than 1. Because if p is less than or equal to 1, well now notice that if this was just 1, if I take the antiderivative of that, what's the antiderivative of 1 over x? Natural log of x, right? And our natural log of x is increasing infinitely. So now it's no longer getting closer and closer to something. Second thing is if this is less than that, right? So like say this is -2, what would I actually end up doing then? If I have an x to the -2 on bottom? We put it on top, right? And so again, I don't have a fraction. Now I just have an x squared, and we talked about that a little bit ago, that's going to have an infinite behavior. So it would also be divergent. Are we all with me there? So this is just a theorem that is helpful for us to keep in mind. Because sometimes you will see questions asked about this as far as like, at what value Like, it would, instead of just a p, it would say, like, you know, a plus 1 or something like that. At what value would a plus 1, would the integral be convergent? And so you would have to solve it to where whatever's in your exponent has to be greater than 1. Yes, no, maybe so. Yeah?
If p is 0, is that just like its own case?
Well, if p is 0, anything to the 0 power is
1. So
1, so I should have 1 over 1, so I just have the integral of 1. So that would just be a horizontal line, right? So it would also not work, because that's also going to have an infinite area. So speaking of, we just kind of talked about this. What's going to happen here? It's going to be infinite area. So again, we want to treat this as 2 separate things. So what we're going to end up doing, so we'll just go through this one quickly, but I just wanted to show you why this doesn't end up working. Okay, I'm going to use up b because it's my top bound. But again, I'm going to treat these as 2 separate questions. So I'm going to come over to the side and just work my integral first. Yes? Okay. So again, we said, what is the antiderivative of 1 over x? Natural log of the absolute value of x, and we are going from 1 to b. Which one do I plug in first? B?
Yep.
Okay, minus the natural log of 1, which is just what? Yeah, it's 0. Natural log of 1 is 0. So I just end up with the natural log of b. But like I said, what does that graph look like? Okay. So we have a vertical asymptote and we are increasing. So now that I've worked my integral problem, I can work my limit problem. So I have, as b goes to infinity, of the natural log of the absolute value of b. As my b values going towards infinity, what are my y values doing? Increasing. So they will also be going towards infinity, which is why this would be divergent. So that one's not super interesting because we end up with something that is divergent. So let's look at one where we're not divergent. So right now, where are we improper?
Negative infinity.
Correct. So we're going to need to rewrite that as the limit as a goes towards a negative infinity of the integral from a to 0 of x e to the x dx. Yes, no, maybe so.
Yes.
Are we okay with that so far? And again, we're going to treat these as 2 separate problems because I don't want to write out my limit 500 times. So we're going to come over here and just look at our integral from a to 0 of x e to the x dx. Then I'm going to evaluate my integral, just like we did with our natural log. How do I evaluate that integral? Ah, they do integration by parts. Good practice for us, yeah. So what do we want our u to be?
X.
Okay, which means that my du is
Dx.
dx. So our dv is going to be e to the x dx, which means that our v is just still e to the x. So this is gonna equal, so what's our first part give us?
UV.
Okay, so our u is x, our v is e to the x, and remember we need to be careful here about putting our bounds on, because I've now evaluated that part, minus, what comes next? The integral from a to 0 of e to the x times dx. Well, that's nice, because what is the antiderivative of that? Just an e to the x, and now we're evaluating the whole thing from a to 0. So we all okay with that? Okay. So then which one do we plug in first? 0. So I have 0 times e to the 0 minus an e to the 0. And then what are we plugging in? A. So I have a e to the a minus e to the a. Simplifying there, 0 times anything is just going to give us 0. So this first one goes away. However, be careful, because this is where some people tend to drop stuff off when they shouldn't. What is e to the 0? 1. So I have a negative 1 there. Okay. And then I'm going to go ahead and distribute our negative. So I get minus a e to the a power plus e to the a. Yes, no, maybe.
Yes.
So far, so good? Okay. So then now that we have evaluated our integral, I can come back over and work my limit question. Which, not technically, we're not going to count it off, but I'm going to put parentheses just so we're reminded. But remember that as long as I have addition or subtraction, we are allowed to separate out the limit by that addition and subtraction. Because what is the limit as a goes to negative infinity of -1 going to be? Just -1, right? It's a constant. The limit of a constant is just that constant. Yes, so I will just end up with a -1. Yes, no, maybe. The other one that is also fairly easy is my e to the a. Because if we think about what is the graph of, again, a is acting as your exponent. So what does the graph of e to the x look like? Exponential. And exponential. Okay. But we're going to what direction? Negative infinity. So what does e to the x get closer and closer and closer to as we go to negative infinity? 0. Are we all okay with that? So like this one would also go to 0. So then I just have to subtract off this middle part. I'm going to pull out that negative because it just makes my life a little bit easier. But I haven't evaluated this limit yet. So I still have to figure out what that is. Are we all okay with that? Yes, no, maybe? Okay. Now we do need to think about, so if I plug in a negative infinity to an a, and we can't plug in negative infinity, but we're thinking about it, right? I would get negative infinity. We just said that e to the negative infinity would technically be 0. So I have a negative infinity times a 0. What is that?
Sure.
It is not.
Oh, wait.
What? I don't know. That's a valid response because that is an indeterminate form.
Oh.
Right? Just like if I had infinity times infinity, infinity times 0, right? Because we want it to be 0, but we also want it to be infinity, which is why it's indeterminate. Yes? Okay. So what do we like to use when we have things that are in indeterminate form? For limits. L'Hopital's, alright, but L'Hopital's only works if it's what?
Fraction.
A fraction, right? Okay, so we're in an indeterminate form, so we want to use L'Hopital's, however, we need to rewrite it as a fraction. Are we okay with that? In order to apply L'Hopital's? Yes, no, maybe. There's a lot going on in this question, I get that. We're pulling out all the previous information. Great. It's like it all adds up together. Alright. So, kind of what we were talking about with our p-value stuff. Are we all okay? That would also be true.
Yeah.
If I make it negative, I can put it in the bottom. But that is now the same thing as my previous one. Yes, no, maybe? Okay, so up top, I still get a negative infinity, yes? But now, notice on bottom, this would be negative infinity, which is just positive infinity. And e to the x goes towards positive infinity as x goes towards infinity. Agreed? So now I have technically it's negative, but infinity over infinity. Agreed? Which is also an indeterminate form, but now that it's a fraction, we can apply L'Hopital's rule. So what does L'Hopital's rule tell us to do?
Derivative.
Take the derivative. Now, we do want to be careful here because we're taking the derivative with respect to a, okay? A is acting as our variable, okay? It's not a constant a, it's a variable a. Are we all with me there? Okay, so what is the derivative of a if it's my variable? What? What's my derivative of e to the negative a? So you have to do a chain rule, right? Because e to stuff, what's the derivative of e to stuff? E to the stuff still. And then what's the derivative of the negative a? Negative 1. Yes, no, maybe. Are we okay with that? So, I can go ahead, I'm going to factor out this negative as well. So I end up with a positive now. Negative infinity. 1 over e to the negative a. Well, we just said a second ago, again, we can't plug in, but if I think about it as plugging in, if I plug in a negative infinity, I would have negative infinity, which is positive infinity. And what does e go towards as x goes towards infinity? Also infinity. But if that's on the bottom, then what is 1 over infinity going to be approaching? 0. So I get negative 1 plus 0. So we just get negative 1. Which means that this equals negative 1. Now, would this be the type of question that you're going to get every single time? No. Okay? Kind of like on our last one that we just did, I could definitely give you something in here where your integral is just going to be basic integrals, right? Like a natural log, like you get a natural log, right? A basic trig one, basic power, things like that. Those are going to work pretty straightforward, okay? So not all of them are you going to have to do parts, okay? But that is a good reminder for us about parts. Also, as we come over to the limits, a lot of these limits are going to be a little bit easier, okay, than what we did here. But also, this is a good reminder of that we can apply our L'Hopital's rule when we are looking at limits. So, would I give you something that combines this many things on a test? No. Okay, but it is a good reminder of all of those things for this particular problem. Because then it hits all those birds with one stone. So now if you see any one of those things in a question, hopefully you can do those. Do we have any questions on that one?
If it's negative infinity to infinity and you break it apart, you put that same equation in both?
Okay. And we'll look at one like that tomorrow. Okay. We're just running short on time, so we're going to stop here for today. But we will have another example tomorrow.